All right, let's just dive right into this explainer and explore what I think is a totally fascinating question. Have you ever stopped to wonder how your body manages to take wildly different foods, say a piece of plain morning toast, a big juicy steak, or a rich avocado, and somehow turns them all into the exact same usable energy? I mean, we eat such a huge, staggering variety of things, yet on a cellular level, our bodies are running on the exact same fuel. It's a literal miracle of biological engineering. So today, we're going to break down exactly how your body actively swaps that fuel to keep you alive and moving.
To really get this, I want you to think of your body as this massive, hyper-efficient traffic hub where raw materials are constantly arriving, getting sorted out, and expertly routed to exactly where they need to be. Every single bite of food you consume has to go through this central sorting facility. And it doesn't matter if you just ate a huge Thanksgiving dinner or if you're skipping lunch entirely. This hub is grinding away 24/7. It's constantly making the call on whether to burn energy right now, pack it away for later, or pull from emergency reserves just to make sure your vital organs never shut down. To figure out this incredible hub and spoke system, we'll be looking at 6 key areas: the metabolic crossroads, the universal energy bridge, storing excess as fat, making sugar from protein, the fat-burning flame, and finally, the emergency backup plan. Let's get to it. Okay, Section 1, the metabolic crossroads and incoming fuel traffic. No matter what your specific daily diet looks like, the fuel you take in basically arrives in one of 3 main forms. We've got carbohydrates, like bread or an apple, proteins, like that steak or some beans, and fats, like olive oil or avocados. These are your primary macronutrient inputs. Now, they obviously look and taste completely different on your plate, right? But they are all headed to the exact same destination inside your cells. As soon as you chew and swallow, your digestive system starts ripping these whole foods apart into their smallest, most basic building blocks. Carbs get broken down into simple sugars like glucose, proteins get dismantled into amino acids, and fats, they're separated into fatty acids and glycerol. These tiny components then flood into your bloodstream, basically entering our biological traffic hub as incoming cars, all racing towards your cells to give you energy.
Which brings us to Section 2, the universal energy bridge, or what we can call the metabolic toll booth.
Slap bang in the center of our metabolic map sits acetyl-CoA. This molecule is the universal energy bridge. The source material is super clear on this. Absolutely every single macronutrient, whether it started its life as a carb, a protein, or a fat, has to convert into this one specific intermediate molecule before your body can enter the energy-producing citric acid cycle. To really wrap your head around this, just think of acetyl-CoA as the ultimate metabolic toll booth. Right past this toll booth is the citric acid cycle, the Krebs cycle, which is essentially the cellular engine cranking out ATP. That's the literal energy currency of your body. Everything you do, from blinking your eyes to running a marathon, takes ATP. But you absolutely cannot make that cellular energy without crossing this one specific bridge first. All that chaotic, diverse traffic of glucose, amino acids, and fatty acids, it's all forced into this single, highly regulated lane.
Moving to Section 3, storing excess as fat through the lipogenesis pathway. This specific pathway is called lipogenesis. Step 1 happens when you eat a big meal and your glucose levels shoot up way past your immediate energy needs. Now, why does this matter to us? Well, because this is the actual biological mechanism behind weight gain. When you eat a massive meal and then just kind of chill on the couch, that universal energy bridge gets completely backed up. You basically have more traffic arriving at the toll booth than the cellular engine can actually process. So step 2 kicks in. Your liver basically says, okay, let's pack away this extra unused acetyl-CoA, and it converts it into triglycerides, which is fat, for long-term storage. Now, evolutionarily speaking, this is pure genius. For our ancient ancestors who genuinely didn't know when they'd find their next meal, storing that excess fuel for a rainy day literally meant the difference between life and death. But today, with food practically everywhere, this incredibly efficient saving mechanism is usually what leads to unwanted weight gain, just because we keep overloading the toll booth and our bodies dutifully pack all that excess away as fat.
All right, Section 4, making sugar from protein via the gluconeogenesis pathway.
There is just an incredible contrast between lipogenesis and what happens during a fast. We literally just saw how the body handles a feast by hoarding excess fuel. But what happens when you're fasting? Maybe you're intermittent fasting, or you're just waking up after 8 hours of sleep. When your blood sugar drops, your body doesn't just call it quits and shut down. Instead, it literally throws its metabolic pathways into reverse through a process called gluconeogenesis. Even the word itself basically means the creation of new sugar. When there are 0 carbs coming in from your diet, your body grabs amino acids from protein, mixes them with glycerol, and synthesizes fresh glucose right on the spot. Your body is practically manufacturing its own sugar from scratch, and this is an absolute must-have survival mechanism because certain parts of your body, especially your red blood cells and parts of your brain, strictly demand glucose to function. If you don't eat it, your body will creatively build it just to keep the lights on. Let's look at Section 5, the fat-burning flame and carb dependency.
Now, this might sound completely counterintuitive to some of the common narratives you hear floating around the diet world, but based on the core metabolic pathways we're looking at, to efficiently burn fat, your body actually requires carbohydrates. Carbs literally ignite the fat-burning flame. Let's look a little closer at why that's an absolute chemical necessity. It all comes down to this really fascinating biological two-step dependency. In step 1, the normal breakdown of carbohydrates produces a specific byproduct called oxaloacetate. Why does that matter? Well, because that exact byproduct is non-negotiable for step 2, where you actually process the fat-derived acetyl-CoA in the energy cycle. Think of it like trying to build a campfire. The fat stored in your body is like these massive, dense logs of wood. They hold a huge amount of energy. But the carbohydrates, those are the kindling and the spark. The oxaloacetate is literally the chemical spark that catches fire. You simply cannot ignite and efficiently burn those massive logs of fat without the spark that comes from breaking down carbs. They are just intrinsically linked in the metabolic machinery. Without that carbohydrate byproduct, the fat-derived fuel just hits the toll booth and totally stalls out.
Which naturally brings up a huge, glaring question. It creates this fascinating dilemma for our biological traffic hub. If carbs are the essential kindling and flame required to burn fat, what on earth does your body do when the carbohydrates run completely out? If that spark is entirely gone, how do you keep the vital organs running? And that takes us to Section 6, the emergency backup plan, otherwise known as entering ketosis. When there just aren't enough carbohydrates in your system to fuel the normal cycle and give you that essential spark of oxaloacetate, the normal cellular engine stalls. For most of your body, this is okay. Your muscles can find other workarounds. But your brain consumes something like 20% of your body's total energy, and it desperately needs a constant supply to survive. The huge problem here is that regular fatty acids cannot cross the blood-brain barrier. The brain is walled off and isolated. So your liver initiates this incredibly elegant emergency backup plan called ketosis. It takes those fats and converts them directly into much smaller molecules called ketone bodies. These ketone bodies are super unique because they can totally bypass the stalled cycle, travel through the bloodstream, and easily slip right past that blood-brain barrier. They act as a highly specialized emergency fuel designed specifically to keep your brain functioning during periods of severe carb restriction or even starvation. And actually, this is the exact metabolic state that popular diets like the keto diet are intentionally trying to trigger. So, when we zoom back out and look at the entire metabolic picture, we can really start to appreciate the dynamic adaptability of our biological factory. I mean, just think about the extremes it manages flawlessly every single day. Whether it's handling a massive holiday feast by neatly packing away the excess as fat for later, surviving a famine by ingeniously turning muscle protein into fresh sugar, efficiently burning body fat using a required carbohydrate flame, or pulling the absolute emergency ripcord with ketosis to keep your brain alive. It all happens seamlessly. All of these wildly different scenarios, these completely different dietary inputs, are dynamically managed and routed from just one central vital bridge, acetyl-CoA. Knowing exactly how these 4 distinct exits work, it really makes you stop and wonder, doesn't it? As you go about the rest of your day and look down at your plate, think about that universal energy bridge and the incredible, complex machinery inside you. Based on exactly what you're about to eat for your next meal, which metabolic pathway is your internal traffic hub going to be forced to prioritize next?